welcome to video lesson 2C-2. We're going to start off with just a little vocabulary. We only have one word to add to our glossary today, and that is linear function. We've talked a lot about linear functions in both 2A and 2B, and now as we've begun 2C into it as well. But we wanted to make sure that we took the time and gave you guys a formal definition for this. So a linear function is a function with a constant rate of change and a straight line graph. So before we move on any further, please make sure you have that copied down into your glossary. Pause the video if you need to. And now we can go ahead and move into our notes for the day. So in 2C-2 we are going to be talking about function notation. Our learning target is that I can read and write functions in function notation. So relations can be expressed in several different ways. And what relations do is take two different variables, usually one is going to affect the other, and they're going to link them in some way or relate them. So we have a relation that we're given here with ordered pairs. That's the first way that we can write a relation. We can write them in ordered pairs. We have 2, 3, 4, 7, and 6, 8. We can also display in a couple different ways. You guys are used to seeing XY tables by now. So what we're going to do is we're just going to put our X values into the X column. And we're going to put our Y values in the Y column. Alright, another way that we can display this relation is by graphing. So we would graph the ordered pair 2. So we go right 2 and up 3. And we put a dot there. And that would represent my first ordered pair. We could do the same with 4. We go right 4 and up 1, 2, 3, 4, 5, 6, 7. And we put another dot. And we can do a point at 6, 8. 1, 2, 3, 4, 5, 6. The last one we went up 7, so we're just going to need to go up one higher here. And so this is a third way that we can show this relation. And the final way is to use a map. You may or may not have seen this in middle school before. What we are going to do is we're going to list our terms in the map. Now, we only have to list each value once. We're going to put our x's here and our y's here. If we were to say have 2 2's in this set, we would still only write the 1 2. We only need to write each number once, and we usually go in ascending order. So we start with the lowest number and work our way to the highest number. I'm going to do the same thing with the y's. Now these don't necessarily have to match up directly across. We're going to put them in ascending order just like before. Now what I'm going to do is I'm going to look back at my ordered pair or my XY table. I find it easy to look back at the XY table. But we're going to draw an arrow connecting each X value to its Y value. So 2 should connect to 3. 4 should connect to 7. And 6 should connect to 8. Now in this case, this was a pretty neat and clean one where they went straight across. Sometimes you might see arrows going diagonal, or you might see 2 arrows going from one to another. For example, if we had 2 twice, we would have a 2 that went both to the 3, and whatever the other ordered pair was. Alright, so that's 4 different ways, ordered pairs, an XY table, a graph, and using mapping, that we can display a relation. So, we are going to look at functions today in function notation. And a function is a special type of relation that pairs each domain value, or x value, with exactly one range value. So each domain, each x value, will match with only one y value. Now you'll often see this illustrated by a function machine. And the way a function machine works is you are putting something into the machine does a specific operation upon it, and it spits out some sort of output. So for example, we might have a function machine that is 2x plus 1. Now whatever we put in would be filtered through this. So let's say that we put a 3 in our input. So we would plug that in for our input. We do 2 times 3 plus 1, which is of course going to give us 6 plus 1, better known as 7. And that's going to be our output. So we put a 3 in and we get a 7 out. Now with a function, no matter what, when we put in our input, we're only going to have one possible output. If we were to be able to put 3 in and get 3 or 4 different choices, then it wouldn't be a function. Each domain only spits out one range, or each input only spits out one output. So you might see that visual from time to time when we're talking about functions. Alright, so we're going to go ahead and look at two examples. We want to give the domain of the relation and tell whether the relation is a function or not. And we want to justify our answer. Now, to me, one of the easiest ways to tell whether something is a function or not is to put it in the map form when we're given ordered pairs like this. So what I'm going to do real quick is I'm going to draw myself a map, just like we did in the example earlier. And I'm going to fill in my x's and my y's. So remember, I put them in ascending order, and I only have to list them once. So even though one happens more than one time, I'm just going to list it once. Alright, then I have 3 and I have 4. Now for my y values, I start with a -2. I have a -1, a 0, and a 1. Now before we go further, I want to point out this has just separated our ordered pairs into our domain and range. We can tell that our domain is going to be those values in the x's. Now, when we are using a discrete function like this, where it's a bunch of ordered pairs and not a continuous line, we use brackets to indicate our domain. So our domain is going to be the numbers in here. Again, just like when we wrote it in the map, we don't use the numbers that repeat. So even though one was used twice, we only have to write it here. So I'm going to close my funny looking brackets now, and that's going to give me my domain. I'm going to do the same thing for range. I use the same brackets for the range, and I have a -2, a -1, a 0, and a +1. So now I have my domain and range just like we were asked, and I'm going to go ahead and finish my mapping. So if I look at the 1, I would need to connect to a -1, but I also used it with a +1, so I'm going to have to draw an arrow down here as well. Now for my 3, it was connected to -2. And finally, my 4 was connected to 0. Now I have to look and remember, for it to be a function, each domain can only have one range value. But when we look here at Mr. 1, he matches up with two different ranges, which is a no-no for functions. So we're going to say that this is not a function. And our reasoning is going to be that the 1 in the domain matches more than, I'm just using the greater than symbol there for shorthand, but it matches more than one y value or range value. So we are going to have to say, like we said, that this is not a function. Now another way that we can quickly tell sometimes is by looking at how many elements or numbers we have in both the domain and the range. Notice in the range we have 1, 2, 3, 4 numbers, but in the domain, since we eliminated the ones that repeat, we only have 3. So that means for our domain to be able to match the range, one of these somewhere would have to be used twice. So since we have a larger set of numbers in the range than we have the domain, we also can tell from there that it's not a function. Alright, let's look at one more example of this. And I'm going to try and do this one without the map so that we can see that you can still do this without having to draw the map every time. That's just a helpful hint if you're having trouble separating the domain and range. So we want to give the domain and range of the relation and tell whether the relation is a function again and justify our decision. So let's look at the domain. Domain is x values. I'm going to start off with my beautiful little butterfly brackets. And I'm going to list the numbers that I have. So I have a -1. I have a 0. I have a 3. And I have an 8. Alright, so that's my domain. Pretty simple. If we look at our range, I'm going to have, let's see, I got a -9. Now I have two 4s, but I only have to write them once. And then I have a 7. So I have my domain and range. Now this time if we look at our domain, we didn't have any repeats. No domain went with more than one range. Now, we did have two ranges that match with one domain, but that does not mean it's not a function. Remember, our function rule was that the domain couldn't match more than one range. The range, however, can match up to as many of the domains as we want. So in this case, we're going to say, yes, it's a function. And the reasoning is going to be that each domain matches only one range value. All right. So moving on. If we have a graph, we have something called a vertical line test, where if we pass through more than one point on a graph, then the relation is not a function. What you might also hear this called is the pencil test, because what is easy for you guys to do, let's open it up, my calculator hit the wrong button there. Alright, what's easy for you guys to do is take your pencil across a graph and drag it across the graph. Now, if that pencil or if that line crosses the graph more than once at the same time, it's going to be not a function. So if I'm looking at this first example, this is a function because no matter where I move this line across the graph, it's only going to touch one point. Now if I look at the second one, it's going to do the same thing. I can move it all the way across here and I'm only ever touching at one point. However, on this third one, if I'm moving it along, I have several places where I am touching more than once. For example, right here, I am touching right here, and right here. So I'm touching that graph at more than one point on that vertical line. So we're going to say that that is not a function. Alright, so the input of a function is also called the independent variable. We're going to find out that we have a lot of different terminologies that all mean the same thing. The output of the function is also the dependent variable. Now, the value of the dependent variable depends on or is a function of the value of the independent variable. So, the independent variable, or our x value, our input value, is going to affect what the dependent variable is. Whatever our dependent variable is going to depend on what we plug in for the independent variable. So when writing equations for functions, we use a specific format called function notation. Now, the dependent variable is a function of the independent variable, as we said above. Now, we're used to writing equations where we have y being a function of x. When you were graphing, everything was in the y equals mx plus b form. However, in function notation, we write equations like this. Instead of a y, we're going to use the f parentheses x. Now, what that is saying is that this we would say is f of x. Now that f might change. It's kind of like a first name. You might see g of x or h of x or sometimes j of x. But the whole point is that saying f is a function of x. So our input is going to be x, and our function notation, instead of using a y now, we're going to write f of x. So really the only difference between function notation and what we're used to writing is that instead of using the y, we use the f of x now. Alright, so let's take a look at how that is going to affect what we are doing. So if we had the equation y equals 5x plus 9, if we were writing in function notation, we would write this like this. We would take out that y and we would replace it with what we say is f of x. So f of x is equal to 5x plus 9. Alright, so oftentimes we're asked to evaluate functions at a specific point using function notation. Let's take a look at an example. So, if we are given f of x equals 7x plus 2, and we are asked to find f of 2, what we are going to do is similar to in Unit 1, where we were evaluating expressions. We're going to take whatever they give us here, and we're going to plug it in anywhere we see an x. So I'm going to now write, instead of f of x, I'm going to write f of 2 because we're evaluating it at the point 2. Now I don't do anything math related with that. That is just our notation that we use. On the other side, however, I'm going to plug in 7, and then where my x is, I'm going to put in 2 plus 2. Now we are going to go ahead and simplify this. So the f of 2 again is just going to stay f of 2, and we're going to multiply 7 times 2 and get 14, and then we have to add 2. So again, still just leaving this as f of 2, it's going to equal 16. So we were asked to find f of 2. We see now that f of 2 is equal to 16. It's just like one of the ones from Unit 1 where we're plugging in for the variable. We're doing the exact same thing here. This f of x, remember, is just a generic name for the function. This could be f of x, it could be g of x, it could be h of x, it could be really any letter here. We use different letters so that we can tell them apart if we have more than one of them. Alright, the x is the generic name for the input value. That's why we were asked to plug in 2, so we put in the input value. And the whole symbol is the output value, or our y. Remember, this used to be where we would have put y. Alright, so let's continue on. Sometimes you might be asked to find x from an equation written in function notation. For example, if we were given g of x equals 3x plus 3, and it tells us that g of x is equal to 12, we are asked to find x. Notice that this is written differently than examples in the past that we were doing in the last example. Before, we had a number given in the parentheses instead of the whole piece g of x being equal to 12. So since this whole piece g of x is equal to 12, we are actually going to be replacing the whole g of x part of the equation instead of plugging 12 in for x. So we would plug in 12 equals, and we're going to write the other side exactly the same, 3x plus 3. And now all this is a basic two-step equation. We need to get x by itself, so we subtract 3 from both sides. 12 minus 3 is going to give us 9, and we're going to have 3x left on the other side. We'll divide both sides by 3 to get x by itself, and we're going to get x is equal to 3. So when g of x is equal to 12, we know that x is going to be 3. So again, to summarize that up from the difference from the last example we did, since it gives us g of x instead of g of a number, we're going to replace that whole g of x thing with 12. And that works no matter what letter variable that is, whether it's an f, a k, an h, whatever letter that is, we're going to replace the whole block with the 12, or whatever number we're given, and solve for x. So we can also write ordered pairs in function notation. So if we were asked to write the following ordered pair in function notation, remember back to this image that our input is going to be what's inside the parentheses, and the output is going to be the whole thing on the outside. So I am going to write this as f of 9, because that's my input value, I'm plugging that in, is equal to negative 7. All I did is I put the x value inside the parentheses where the x goes, and I know since this is going to be my output at negative 7, that f of 9 is going to have to equal negative 7. Now we can also go the other way around. We want to translate the following statement into an ordered pair. H of 3 is equal to 12. So what we want to do in this case is to go ahead and realize that this is going to be our input value, which is our x value, and it's going to equal our y value. So our ordered pair would be 3, 12. Nothing too difficult, it just can be confusing if you aren't thinking through it in terms of input and output. Alright, so go ahead and pick up application 2C-1 from the Algebra Embassy. The application video can be found directly underneath this video. Alright, good luck and we'll see you in the next lesson.